In this 75th anniversary of World War II, it's appropriate to recognize Frank Caldwell. On every frontline aircraft that the Allies fought had a propeller on it, and it was, 76% of the time was a hydromatic propeller. And so it's great to look at that achievement of his career within the context of World War II, but also to see how it wraps up the story of how the airplane evolved in the decades before World War II. That it took all of these years to really make the airplane what it was and allow the Allies, as well as the Axis, to fight with high-performance aircraft. Allies prevailed is because, in many ways, because of the hydromatic propeller, because it gave the performance, the reliability, and the survivability for Allied crews, especially Americans flying over Europe and in the Pacific. And looking at the achievement of Caldwell and looking at the decades between the Wright brothers and World War II, you see this connection between how the inspiration of the Wright brothers, this generation of engineers trained at the university level, and they're inspired by the Wright brothers and by the airplane and what it can do, and they want to see what they can actually contribute. And Caldwell saw that as a way to contribute to propellers. And every airplane had a propeller at the time, and that was a central element of the technology, and he played a central role in developing it. Frank Caldwell grew up in Tennessee, near Chattanooga and Lookout Mountain. And growing up in the South, he went to MIT for his college education, where he majored in mechanical engineering. And there he investigated one of the first true studies of the airplane propeller. In 1912, his bachelor's thesis, Investigation into Air Propellers, was published. And that knowledge he took back to industry. He went home to work in the family business, porcelain enamelwares business, but he couldn't get aviation out of his head, and he joins the Curtiss Company in 1916. And his first job is to be sent to the Mexico border to help with the single core aircraft that have their propeller blades splitting in the dry, humid environment of New Mexico. And so he investigates local woods. How do you make a propeller better? And so from the very forefront of his career in 1916, he's understanding that the propeller has several limitations in regards to its construction materials as well as design. And he takes that knowledge at Curtiss and moves to McCook Field, which is the U.S. Army Air Services Engineering Division in Dayton, Ohio, and he becomes their propeller expert. And he takes the knowledge of mechanical engineering as well as electrical engineering, working with the Westinghouse Manufacturing Company in Pittsburgh, and he designs the world's first significant propeller testing laboratory. And taking knowledge from electrical engineering, mechanical engineering, civil engineering, he's creating aeronautical engineering, especially in regards to his own specialty. And so the documents at the time called it engineering of a pioneering character. On the standard E-1 biplane of the World War I era, this is a typical wood fixed pitch propeller that Frank Caldwell would have started working with in 1916, 1917. And it's laminated wood and it's fixed pitch, meaning that the angle in which the blades turn through the air stay the same at any speed, at any altitude, any performance condition. And by virtue of his position in McCook Field, Frank Caldwell is in charge of testing every propeller designed for every American plane, whether it's Army or Navy. And he's responsible for refining the designs. So we often think of him in regards to his work on variable pitch metal propellers, but he's also well-versed and very accomplished in the design of wood propellers. And it's that knowledge and the intimate familiarity with wood propellers that leads him to ask the question, can we make something better? There's this very important period from 1926 to 1934 in which the technology that makes the airplane modern is being introduced and tested, and it's being flown. On this Pitcairn mail wing is a standard steel ground adjustable propeller. And this is the first stage of Frank Caldwell answering the questions he asked about the problems with wood fixed pitch propellers. Caldwell answers his questions about the problems of wood propellers, in which he needs a more durable material. He starts with metal. He even looks at Bakelite micarta, but he really centers his investigation on aluminum alloy or duralumin. And so these drop forged duralumin blades are his answer to the lack of survivability over a long time in wood propellers. But he's looking at fixed pitch. And the first step here is to create a two-piece steel hub that you can actually loosen the clamps on it and change the angle of the blades for a predetermined flight condition. If you want to really just set your blade angle for takeoff, you loosen those clamps, you turn the blades, and then you set them back. And you have that. But once you take off, once you get to cruise, you're going to have a racing propeller. But if you want a cruise condition with this propeller, you can set it for cruise at a lower pitch, but you're going to take a very long runway to get off the ground. And so he sees the problems with that, but it's the first step of providing a reliable, rugged, and practical propeller for American aviation. And this is the propeller that Charles Lindbergh chooses to fly across the Atlantic with. He specifically says, I want a metal propeller, and that means a standard steel ground adjustable pitch propeller. The virtue of this being on a Pitcairn mail wing also shows that the mail carriers wanted something rugged, light, and reliable, something that wasn't going to get destroyed over the course of just flying in bad weather. And so this is a cornerstone technology, just like the Wright J5 Whirlwind that's on the Spirit of St. Louis, in which that combination really allows American aviation especially to go to the next level in the late 1920s. The success of the ground adjustable pitch propeller produced by Standard Steel and designed by Frank Caldwell leads to the next foundation in propeller development, which is a two-position controllable pitch propeller. It's variable pitch, in which the pilot in the cockpit can set it for low or high for takeoff and cruise. And so what you see here are these counterweights. And Caldwell has the idea of using hydraulic pressure to push the blades, to change the blades in one direction, but when he wants to change and let off the pressure, these counterweights move the blades in the opposite direction. And so this is a mechanical engineer's way of designing a variable pitch propeller. It's rugged and it works. And this is used on the first generation of American airliners, the modern airliners, the Boeing 247D, the Douglas DC-2. And so the introduction of this propeller, this is the true step in this revolutionary period of technological development in regards to a variable pitch propeller that improves the performance for American aircraft. This Vultee V1A has a constant speed counterweight propeller from 1935. And this is the next step beyond the two-position controllable counterweight propeller that Frank Caldwell and Hamilton Standard introduces and gets the Collier Award for. And this is another level of development and innovation working towards a modern propeller, the hydromatic propeller, a fully automatic constant speed propeller. That it's the same counterweight construction that uses hydraulic pressure for one direction and counterweight or centrifugal force to actuate in the other. But you have the addition of that small black governor, which is on the front of the crankcase of the radial engine. And what that does is it allows engine speed to stay the same, but it varies the hydraulic pressure versus the centrifugal force to change the pitch of the blades when needed by the pilot. And so he works the remainder of his career at Hamilton Standard. It's part of the United Aircraft Combine, the vertically organized monopoly, as some government regulators would say. But he works with United Aircraft through the rest of his career into the 1950s and retires and lives a very lauded life in regards to his importance to the growth of aviation. And so as a specialist and as a person who's excited about aviation, Caldwell was right there at the beginning, and he worked all the way through those very important years of the 20s, the 30s, and the 40s, and the 50s. At the end of his career, he's actually doing turbine research because Hamilton Standard is working on that. But by the time Caldwell retires in the 1950s, the super hydromatic propeller is powering airplanes, especially large airliners and tactical transports. And so there's a legacy there that's very important. And he's not lauded, he's not a household name in terms of aviation, but it's when the American Society of Mechanical Engineers recognizes his work with a landmark on the hydromatic propeller. And then looking at the history of the technical development of the airplane, especially in this growth of specialty, that Caldwell really comes to the forefront as one of those very important figures that we have to study and understand to really understand how the airplane came to be.